welcome to the course Advanced Reaction Engineering. So, in this course we basically will discuss about the catalyst synthesis. So, in reaction engineering we have studied various reactors. So, various type of reactors are available. So, like batch reactor, plug flow reactor, CSTR reactor, packed bed reactors. So, different means relevant problems or associated problems with that particular reactors we have discussed. So, now once we conduct any reactions, so then of course, we have to use a catalyst to perform the reactions. So, therefore, means we need to know means what are the type of various catalyst means or reactions are there, and what are various type of materials or catalyst are there, and how we can prepare those materials as if we can get good conversions, good selectivity, and of course, that good yield of that particular desired product that we are targeting for a reactions, or from a reactions we are means going to synthesize that particular products. So, today basically we will discuss about the type of reactions and representative catalyst and various supported materials, that particularly microporous materials and mesoporous materials, how those materials can be synthesized experimentally, that we will discuss. And after that catalyst synthesis, and then catalyst shapes or formulations, that is also very crucial or important for any means catalyst synthesis, any reactions, reactor design. So, that part we will discuss. Let us say we have a catalyst, let us say this is we can say catalyst. So, nickel oxide or alumina supported catalyst. So, here's nickel alumina catalyst. So, here nickel may be in the form of nickel oxide or maybe in the nickel metallic state, that is zero oxidation state nickel. So, this way we can synthesize the catalyst depending upon our applications, means which particular reactions we are going to use this particular catalyst. In some reactions we can say that nickel zero oxidation state is very active, and that is required for that particular catalyst you have to use for that particular reactions. And in some reactions we can see that nickel oxide in +2 oxidation states, nickel in alumina, that is effective and good for catalyst. Okay. So, now use of catalyst and the type of reaction. So, basically we have discussed, let us say we are conducting these reactions here it is called CO2 reforming reactions or CO2 and methane, that is the reactants. So, we have to maintain this, let us say this temperature and pressures, and we have to put some catalyst. So, here we can choose this catalyst, let us say lanthanum nickel iron oxide catalyst. So, this we can say it is a perovskite type of catalyst it is called. So, the catalyst is synthesized by Sol-Gel method. So, the catalyst we can use to conduct these reactions and we can get this product. So, for that we have to prepare this type of experimental setups, or we can say that means these reactions we have to conduct, we have to take out the product from the reactions, we have to place catalyst, you have to maintain temperature, pressure. So, therefore, here let us say starting material is our reactants and CO2 that through remain inside of the cylinder. So, through that using MFC a particular fluid we can maintain, so that would be injected in these lines CO2 and methanes, that is the feed lines, and so nitrogen also we can use with these mixtures as a inert components or as a diluent or as a carrier that would carry the reactant molecules, and then it would come this is our reactors basically. So, here we have placed some thermocouple. So, this is the temperature controller. So, through that we can maintain the temperature, let us say here this is the catalyst bed. So, here temperature let us say 800 degrees centigrade is required, and that way once we maintain this temperature here and reactant is passing through this catalyst, then it would, when it is passed through this catalyst bed, it would give product. So, that is hydrogen and CO, that is the syngas. So, this here we have to maintain the temperature, we have to place the catalyst. So, this is furnace, outside there is a furnace, means the reactors, quartz reactors we have used here, and that was placed inside of a furnace, and that through that furnace we can maintain these temperatures. So, then temperature we can maintain, pressure we can maintain the pressures, and we can place the catalyst, and once the system is ready, then product will come out, and then so we have to analyze means how much concentration of products components formations is there, means conversion, selectivity, yields that we have to measure, and for that we have to use some analysis technique, means since all these components are gaseous components CO hydrogen and some unreacted reactants also remain there, means if we consider that 90% conversions is there, so then rest 10% components reactants remain with that reacting mixture or the product mixtures. So then that we have to inject here in that GC to find out means how much concentrations of the individual components are there. So these concentrations we can measure with the help of GC, and from there we can find out the conversion, selectivity, yield of the products. And since we have used this particular catalyst for this particular reactions, so apart from these there are some other catalyst I said nickel oxide catalyst. This catalyst also we can use for this particular reactions, but always our objective is to develop new better catalyst. So that would be much more effective for that particular reactions, will give higher conversions, higher yield, higher selectivity, more selective to the desired products. So that is the purpose to synthesize any catalysts. So this type of experimental setups we have to, means lab scale we have to study for when reactant is gas and catalyst is solids to carry out any reactions, that is we can conduct. Similarly other reactions also, here also one another examples we are giving. So here also let us say cyclohexane to cyclohexanol and cyclohexanone productions is there. So in that case also we have to build up this type of experimental setups. So where we can feed oxygen and reactants cyclohexanes, so both will come with the inert component nitrogens and pass through this catalyst bed. This is catalyst bed and product will be analyzed with the help of GC, then we can find out what are the components or product formations is there, and like that various means equation or formulas are there. So how to calculate conversion, selectivity of that particular means reactants and selectivity for the desired component. So that way you can find. So here the catalyst is different. So reactions when it is different, catalyst is different. See here iron manganese catalyst was used and earlier lanthanum nickel iron catalyst was used. So in both the cases reactions are different. So of course catalyst is also different. So now there are various type of reactions are available, and means depending upon the our desired product. So target product based on the reactions, target compound, starting materials, everything are different. At the same time catalyst is also different. Here alkylations and dealkylation reactions, when we have in subaromatic compounds. So we want to place once this type of alkyl group insertions in that ring. So then this type of FC reactions it is called. Here AlCl3 type of catalyst we have to use. So similarly isomerization reactions, normal pentane to isopentenes if you want to prepare. So then acid promoted platinum alumina catalyst or acid promoted alumina catalyst we can use for this particular reaction. Similarly dehydrogenation reactions, hydrogenation dehydrogenation reactions, for that we can chromium catalyst we can use, calcium nickel phosphorus catalyst we can use, oxide phase. So here is one single bond to here two double bonds. So butadiene formations, butene to butadiene formations. So dehydrogenation reactions. So here catalyst is different. Similarly oxidation reactions I said this catalyst we can use, and here dehydration reactions, dehydrations. So basically we have taken alcohols in presence of alumina or MgO that acts as a sometimes catalyst. So it helps to dehydrations, means water removals from these compounds. So olefin formations is there, so that we can use. Similarly here's alkylations reactions I already said. So means benzene to ethyl benzenes and then dehydrogenations to styrene formations that we can use this type of reactions. Here catalyst is also nickel catalyst, or here acid treated aluminum chloride catalyst we can use. So here we can see that one reaction to another reaction. So catalysts are not the same. So depending upon that reactions catalyst you have to prepare different type of catalyst. Okay. So, now types of catalyst and this about that properties or how we can synthesize the catalyst. So, means I said when a catalyst we are talking about. So, let us say nickel oxide alumina catalyst. So, here two components are there. Here you can see that this is alumina and over that nickel oxide, this is nickel oxide that is distributed. So, here this nickel oxide that is the means catalytic component. So, catalytic agents or catalytic active sites you can say sites. So, nickel oxides and alumina acts as a support materials, that is actually inert component for the a particular reactions may be. So, this is called support and this is active site. So, mainly this take part in the reactions to increase conversions, yield, selectivity, and this alumina that acts as a support means that helps to distributions of this nickel oxide. So, if you do not use this alumina, so then we can prepare also from the precursors, we can directly we can prepare nickel precursors or salt you can say directly if you heat up. So, then you can directly prepare that, but here's that active sites would be comparatively less than this type of catalyst. So, it would be better than this is not good. So, this would be better. So, here the reasons we will discuss, means why this catalyst is better, why it is not better. So, both the cases nickel oxide is there, but here additionals means inert materials alumina was used. This type of materials is called support. So, it has large surface area, means in this case we are not using. So, here this alumina, let us say it has a large surface area. So, there we are distributing the nickel oxide at smaller size. So, then number of active sites will increase. So, this is the nickel oxide, this small site. So, then number of sites when will increase, then of course, catalytic activity, conversions, yield, selectivity will increase, and in this case maybe it is bulk formations of the catalyst, or you can say bulk nickel oxide formation. So, nickel oxide is there, bulk nickel oxide. So, here number of active sites is comparatively less than this type of catalyst. So, therefore, so these are the things how we can means once we synthesize a catalyst, how to measure number of active sites, surface area, these are the things will and other properties of the catalyst we will discuss. So, now types of catalyst if we see or talk about. So, there are homogeneous catalyst and heterogeneous catalyst. Homogeneous catalyst when catalyst is in solutions and reactants is also means both catalyst and reactant both are in the same phases, that may be catalyst is liquid form or gaseous form, reactant is also gaseous form and liquid form. So, then these are the type of reactions which called homogeneous catalysis, and when heterogeneous catalysis, when catalyst may be in the form of solids, solid phase, catalyst is solid phase, and reactants that are in the gas or liquid, both are different phases. So, this type of reactions is called heterogeneous catalysis, and mostly we will discuss heterogeneous catalysis means reactants and products or catalyst both are in different phases. Okay. So, based on that heterogeneous catalyst we can say it is a porous catalyst having high surface area and pores are available. So, these are called porous catalysts. Molecular shifts, sometimes pores are so small that small molecule may pass through this catalyst beds and larger molecules do not pass through that. So, these are example you can say ZSM5s or Geolite type of catalyst. So, or molecular shifts. So, that sometimes used for isomerization reactions or cracking reactions. So, that we will discuss. Monolithic catalyst. So, that is used for where pressure drops and heat removal are major considerations. This type of catalyst or catalyst bed is used, monolithic type of support materials or catalyst. So, here the features is honeycomb or porous type of channel is there, so many channels are there, hexagonals or rectangular. So, through that we can place the active sites and then that way we can design the catalyst. Some supported catalyst I said already. So, support materials is used and with that the active sites will be dispersed, and unsupported or bulk catalyst, that is I already discussed, nickel oxide is bulk catalyst and this is supported catalyst. So, here these are the catalysts. So, here means active sites in the catalyst. If you look into that, most of the catalyst contains so many transitions metals. So, that may be cobalt, iron, nickel, copper, vanadium, manganese, many metals are there. So, that metals acts as a active sites in the form of metal oxide, metal zero state or metal sulphide, metal phosphorus combinations or bimetals, two metal oxide combinations. So, many way it is prepared or means synthesized or developed that particular catalyst. So, this is the called catalyst. So, this way we can say means in different metal oxide state, that way we can say that that particular metal is active for that particular reactions. And various support materials also we can use to prepare that supported catalyst, maybe alumina, silica, magnesia, MgO, titania, ceria, zirconia, geolites, MOFs, alpo 34, MCM 41, SBF 15, activated carbons. These are the materials. So, few I means discussed. Apart from that, there are so many various combinations, two metal oxides, means maybe alumina, silica at different ratio, or maybe ceria, zirconia, both the metal oxides combinations acts as a support material sometimes. And sometimes this means in when it is supported catalyst, these supports would be used large quantity, means maybe 80%, 70%, 90% in 1 gram of catalyst or 1 kg of catalyst. So, this is major quantity is this, and sometimes these materials we use very small quantity, maybe 5%, 2%, 1%, then that metal oxides acts as a promoter. So, these oxides sometimes use very less quantity we are using to improve the catalytic activity, means by that way we can change that particular catalytic property, maybe acidic properties, basic properties or some other properties we can improve. So, by that way the catalyst may be much more better or active or much more selective, conversions will be more. So, that way you can see means that is the role of promoter. Sometimes bulk catalyst having low surface area, why we are not using. So, this type of catalyst, bulk catalyst sometimes has good stability, but sometimes it is has low surface area, means 0 to 1, 0 to 5. So, within that surface area. So, then we can this called bulk catalyst, and sometimes supported catalyst having high surface area, means 100 meter square per gram, 200, 300, 500, 700, 1200 also we can achieve. So, then called it is supported catalyst. So, therefore, this is the basic difference in between these two catalysts. So, therefore, sometimes we prefer supported catalyst for a particular reaction, sometimes we prefer bulk catalyst for a particular reactions. And also mesoporous support also sometimes we use to prepare the supported catalyst. So, mesoporous, microporous support also we can use to distribute the active sites. So, why we choose this type of support? So, these are the support materials. Apart from that, geolites, MOF also we can use as a support materials, or MCM 41, SBF 15s we can use as a support materials. So, this type of materials sometimes having micropores, mesopores. So, that helps in distributions of means active sites also for reactions, diffusion, dispersion. So, that also helps. So, therefore, we use different supports. Okay. So, now process parameters for catalyst synthesis. When we will synthesize a catalyst from its starting material, or we need the precursors, metal ion salts. So, then precursors or metal ions, that is, let us say if we use nickel oxide catalyst. So, then we have to use nickel precursors, nickel nitrates, this type of salts we can use, and alumina powders we have to use. These are the starting material. So, these are the called precursor salts. So, its concentrations, different concentrations we can use as per our requirement or as per our target catalyst that we are going to synthesize. So, it concentrations means we have to make a solutions, means let us say that we have to put it here, here we can take let us say water. So, in water we have to dissolve that salts, and then that salt we have to disperse, or we have to mix up with the alumina, and then by step process final catalyst we can prepare this. So, that we will discuss. So, means this is the way. So, means precursor concentrations means low concentration, high concentration we can take depending upon the concentration we want to load over that support. So, that is important concentrations, precursor selections, precursor concentration. Sometimes temperature is also very important, means the when catalyst we are preparing, it is going or passing through so many steps. So, means drying, calcinations, means sometimes we need to remove the moistures, organic components present in that, means here not only these nitrates, with that some organics means binders or maybe structure directing agents or means surfactants we sometimes use to disperse or distributions of the metals over the surface of the catalyst. So, those the material means remove organic materials sometimes we need to remove. So, then we need to maintain or calcine that catalyst in presence of oxygens or some other gaseous environment. So, to remove those things. So, then say it means at what temperature we should do that. So, that is also important, means let us say 300 degrees centigrade we can maintain, 500 degrees centigrade, 700 degrees centigrade, any temperature we can fix. So, the temperature is also one of the major parameters or components when we are going to synthesize a catalyst. At the same time pressures also, means when we are going to synthesize a catalyst by considering a particular methods. So, then we can conduct, means the operations are 1 atm pressures, 10 atm bar or pressures or 30 atm pressure. So, like that any temperature pressures, with the temperature pressure also we can vary. So, then based on that also catalytic properties or material property also will vary. At the same time stirring speed or mixing. So, when we are taking that solutions with that alumina or some other materials we are mixing. So, then stirring is also important. So, stirrers or stirring speed. So, then solvents also important parameters. So, waters mostly used, that is the cheapest one. So, distilled waters or double distilled waters or millipore water sometimes is used to synthesize the catalyst. Sometimes organic solvents, let us say methanol, ethanols, benzenes, diethyl ethers. So, these are the means acetonitriles, many compounds we use as a solvents to prepare the catalyst, and sometimes pH is also very important. So, the pH sometimes we need let us say 5 pH, and sometimes for a catalyst we need let us say 9 pH is required. So, depending upon that, so we can maintain by changing the pH of the solutions when we are going to prepare a particular catalyst. So, that also another parameters we should look into that, and others parameters maybe filtrations, grinding, so many steps are there. So, that also are depending upon the method of preparations the catalyst we are going to prepare. Okay. So, in the supported catalyst, so various methods are available. So, that is precipitations methods, incipient wetness impregnations method, wet impregnations method, sol gel methods, templating method, the templating, hard templating or sub-templating method, and many others methods are also available. So, depending upon the I said the requirements or the purpose of where we are means applying that catalyst and which particular reactors we are using. Sometimes some sensor is used, there is also some catalyst films is required, very small quantity. So, depending upon the applications purpose where we are applying or using that particular catalyst, the method of synthesis some changes are there. So, that way it is done. Okay. So, now these are the means method precipitation, co-precipitation method, IWI method, WI method, sol gel method, templating method. These are the things we will discuss later. So, before that, so I said whenever we are going to prepare a supported catalyst, support preparations is very important, means on the basis of support, means support plays a very crucial role. So, when we are going to prepare a catalyst, since the metals we are dispersing over the surface of the catalyst. So, I said nickel oxide that we are dispersing over this support. So, nickel oxide also we can disperse over this support. So, both the catalysts are different. So, here silica was used, here alumina is used. So, both the catalyst supports are different. So, depending upon that, so sometimes MgO also we can use as a support, I said. So, depending upon that support property, the catalyst property also will change. Okay. So, then how this support property means, in that support I said there are so many pores are there, and the supports having let us say 100 meter square per gram or 200 meter square per grams or 300 meter square per gram. So, that is the surface area or BET surface area. When catalyst having different surface area, so then the supports having different depending upon that support. So, how means supports having different surface area, that depends on the porosity of the supports. Also the support stability is very important. Sometimes support is having highly porous supports, means 1000, 100, 1500 meter square per grams or thousands meter square per gram surface area is there, but the support stability is not good. So, as compared to this type of fringe, sometimes whenever we are going to use that catalyst for a particular reaction, sometimes the high temperatures we have to maintain, let us say 1000 degree centigrade. So, at this 1000 degree centigrade, maybe the catalyst we have prepared using the support having 1000 not very stable, decomposed easily. So, as compared to the 100 meter square supports, meter square per gram surface area the supports having, that is better. So, of course, we will choose these supports as compared to this, since the support is not stable at high temperatures. So, depending upon that also we have to choose. Sometimes we go for a support having high surface area, that is would be good, that is good, but support stability also important parameter we should know. Okay. So, now mesoporous material support that we can prepare by using soft templating methods or hard templating methods. The mesoporous supports usually prepared. Geolites also sometimes we use as a support material. So, nanoporous materials. So, all those materials whatever we are preparing or we are going to discuss. So, mostly these are called nanoporous materials, because the pores, I said this is let us say support materials or catalyst materials. So, here these are the called pores. These pores may be different type of pores. It may be is this is macropores, this is micropores, and this is mesopores, and this is micropores. So, depending upon the pore diameter, I already have discussed pores, we can classify macropore, mesopores, micropores. So, depending upon the pore diameter of the macropores, maybe it is diameters greater than 50 nanometers. So, 50 nanometer to 100 nanometer. Mesopores the diameters may be 2 to 50 nanometers, and micropores the diameters of that particles. So, that would be less than 2 nanometers. So, diameters of that pores should be this. That way you can classify a particular materials. Okay. So, here you can see various nanoporous materials or support materials I am showing. So, here this is highly porous block formed ceramic catalyst or high porosity block formed ceramic catalyst, that pores diameter is 1 nanometers in this case, and here alpha 34, alpha 5 molecular sieve type of catalyst. So, here catalyst having these are the pores present in the catalyst. Monolithic type of catalyst support materials. So, these are the called monolithic. So, it is this type of rectangular means pores are available. So, it is in the form of channels. Okay. So, like that. So, these materials we can use as a support materials. So, where pressure drops and temperatures effect is very crucial for design the reactors and catalyst bed preparation. So, then sometimes this type of means here these pores are different pore dimensions. So, here different pore dimensions you can notice. Okay. MCM 41s, SBA 15. So, these are silica, basically silica SiO2 support, a silica support. So, but the method of preparations are different. So, these are also SBA 15, these materials also having hexagonal shapes and cylindrical pores. This type of pore structure is available. So, these are the materials actually mesoporous materials. So, these materials mesopore diameters 2 to 50 nanometers. So, these are the materials. So, is MCM 41 and SBA 51. So, how these materials or support materials can be prepared, that we will discuss. And microporous materials, that is geolite materials or MOF materials. So, these are the particles usually having pore diameters less than 2 nanometers. So, but these are the materials sometimes is very good stable material at high temperature, in some reactions, and therefore sometimes we can choose for geolites, and sometimes maybe when it is low temperature, then MOF we can use as a support materials to prepare a catalyst also, or adsorbents, the depending upon the applications. So, that we can use. So, in this type of materials usually some surfactant or structure directing agents are used to make that pores inside of that catalyst. So, that means these type of materials having high surface area, and some pore also is there, 2 to mesoporous materials having highly porous, and pore diameter is 2 to 50 nanometers. So, within that range. So, now we will discuss about nanoporous materials, how we can classify them. So, that depending upon the pore size, I said nanoporous materials we can classify microporous material, mesoporous materials, macroporous materials. It has pore diameters like this. So, geolites and MOFs usually microporous materials in this class, and MCM41 and SBF15 that are mesoporous materials, and some sponge, cartons, metal oxides having high pores, that is macroporous materials. So, that depends on the porosity, based on our pore size we can classify them, and depending upon the building blocks, means when we are preparing that material, sometimes we use some inorganic materials, some organic materials, or maybe organic, inorganic, both mixed materials we are using to prepare that material. So, then depending upon that also we can classify the materials. Okay. So, how that we are synthesizing, and I said sometimes, so whenever we are creating more pores inside of that supports or materials, so we use some structure directing agent, SDA, or structure directing agents, or you can surfactants. So, depending upon various structure directing agent or templates, so we can use when surfactants. So, then CTAP, SDS we can use. CTAP is this, and SDS is this material. So, sometimes these are the surfactants or surface use materials we can use to make the pores inside of the pore of the supports or materials to develop that pore. So, we can use sometimes non surfactant materials also we can use. So, these are the materials we can use, that way also we can classify it, and the structure directing agents we can classify different way, means it is cationic, anionics or non-ionics also. So, if it is cationic, these are CTAPs usually use, and anionic materials, that is SDS, and non-ionics, that is P123 or F127. So, these are the materials we can use for preparing a particular mesoporous materials or microporous materials. So, that we can use. Okay. So, now if we want to prepare microporous materials, so that solvothermal method or hydrothermal method, so we can use to make that materials usually having micropores inside of that materials or that support materials we choose. So, one is the MOF materials, that is having microporous. So, for that some linkers, organic linkers we need, and metal nodes or metal ions is required. So, for metals we can use any metal salts, let us say zinc, irons, coppers, zirconium, and precursors for organic ligands we can use terephthalic acid, trimesic acid, 2-methyl imidazole. These are the compounds we can use to prepare MOF material, metal organic framework. So, this type of structure would form. So, one metal ions and another organic ligands, that will be form if this type of structures, it calls MOF type. So, depending upon if we use zinc, then it is called zinc MOF. If we use nickels, nickel MOF, depending upon the material precursors we are using, both the materials combined also we can use. So, these are the means precursor that we have to use, means organic linker. So, that is shown here. So, here let us say we are going to prepare nickel MOF. So, first you have to take trimesic acid, in water we make a solutions, and another beakers we can take nickel precursors and distilled water solutions, and then both we have to mixed up in another beakers, both we have to put together, then we can make that solutions, and stirrings will be continue for let us say 10 hours. So, then after some times we can see that some precipitations would be there. So, then we have to means washing, filtrations, dryings. So, then the materials would be dried at 100 degree centigrade, let us say 15 hours 20 hours. Then we can do the carbonizations or heat up. So, then excess organic compounds or other materials will be removed, and stable compounds nickel MOF, that particular having different structures we can synthesize. Okay. So, the structure I said, this is MOF structure. So, this type of MOF structures we can prepare. Okay. So, this is the way of methods to prepare nickel MOF. So, there are, this is hydrothermal method I said, at normal pressures we can synthesize, and high pressures also sometimes we can maintain when we are going to prepare this type of material. So, then we have to use some autoclaves. So, when nickel precursors and organic linkers we can use, and then we have to put inside of a autoclaves, and then we maintain some temperature and pressures. So, then the materials we can prepare, so that is called MOF. So, here you can see it is showing here by changing pH of that materials when it was synthesized. So, different type of by changing different pH it has been prepared. So, all these are nickel MOF, but change the pH was the one of the parameter when it was synthesized, it is showing here. And some others means metal, by using terephthalic acid also this type of metal MOF we can synthesize. Okay. This type of materials having high surface area of 500 to 1300 meter square per grams, but having but the stability is not good. So, if we go for any reactions, let us say 700 800 degree centigrades, then this type of materials is not stable. So, then we cannot go for that. So, when our reactions we conduct, or we have to use that particular catalyst at high temperatures. Okay. Next, geolite type of material synthesis. So, geolites it having micropores. So, porosity less than 2 nanometers usually. So, these are the means compositions of the geolites. So, here some metals is there, alumina and silica tetrahedral link or structure is there. So, that linked up with each other with the hydroxyl groups. Okay. So, this type of geolite materials having high surface area, and these are the materials high temperature, the high thermal stability is there. So, these are the materials having micropores, and it has means tetrahedral silicon alumina structure is there. So, it is stable, much more stable than MOF. So, this is the alumina tetrahedral structures and silica structure, both are combined with a hydroxyl groups. So, this is the structure. So, this is the structure of a geolite sketch. So, you can say that here silica and alumina ratio we can change depending upon the means these are the two main components present in the geolite. So, the ratio usually we can maintain once and 1 to any other ratio also we can change when we are going to prepare that materials. Okay. So, how JSM pipes we can synthesize means using hydrothermal methods. So, in the first step is the gel formations. In the gel formations we can use alumina silica precursors, and we can mix in a beakers, and then so we can make a gel formations, amorphous gel formations. So, here basically in these tips we are removing excess moistures, and the solutions would becomes into the gel, and after that in the second steps we can take a autoclave. So, where we can place the gels and into different part, and at the bottoms other materials also EDA, ET3Ns and water. So, these are the we can put at the bottom part, bottom sections, and then we can maintain temperature for 5 to 7 days, and that way we can keep it inside that materials or gels inside in the autoclaves. So, for 5 to 7 days once we put, the materials will forms, then that materials we have to take out, filter, wash and dry it, and then calcine at high temperatures. So, then this type of silica alumina JSM pipes gel formations would be materials will be synthesized. Okay. So, this type of materials having usually pore size 5 angstroms. So, and pentacyl type of rings or units are there. So, here the JSM pipe structures you can see. So, this type of tetrahedral silica or alumina linkage are there. So, the formation of this type of structure. So, this is JSM 12, JSM 5, JSM 22. So, Faujas XY it is called. So, it has, you can see the diameters of that pore, cylindrical pore is there. So, here's 0.56, less than 1 nanometers. So, these are really micro pores, porous materials. So, depending upon the synthesis or ratio of the silica alumina, so that is different type of structure formations is there, and at the same time different type of pores formations are there, pores. So, these are the way, means different means geolite materials we can synthesize. Okay. Now, we are going for soft templating method. So, that is mesoporous materials or support synthesis. So, usually silica SiO2 commonly used a very support. So, it is the materials we can use, or means it has mesoporous materials having 2 to 50 nanometers within that range of pores. So, these are the materials usually used by using sub-templating method. So, in sub-templating method, so how we can synthesize SBF 15s. So, S being here, first we have to take a precursors for silica, and another one is cell assembly template, or that may be ionic or non-ionic materials we can use. So, here we have to use non-ionic materials, means that is P1 to 3, that is, or PVA we can use. So, these are the materials or surfactants we can use, that these are the materials usually water solubles, and then inorganic precursors, and this self assembled templates will be condensations, and metal template composite formations would be theirs, and after that these templates or assembled or template organic components we can remove by heating. Okay, if we heat up, so then only these inorganic structures would be theirs, that with the formations of 2 to 50 nanometers diameters pore formations is theirs. Okay. So, therefore, this type of materials this way we can prepare. Okay. So, here's also you can see, so the same things we are showing here. So, here's P1 to 3 and TEOS we have taken. TEOS is the tetraethyl silane orthosilicates. These are the as a source of silica we can say, these are the as the source of silica, and these are surfactants, condensation, hydrolysis, condensation, this type of structure formation is there, and after calcinations only the silica units SiO2 formation, that is called SPF 15s. So, here it is called SPF 15 because it is non-ionic surfactants we are using. If it is ionic surfactants, so like CTAPs if we use, so here also TEOS is used, and CTAPs is used as a surfactant or self assembly material. So, then by using these steps we can form the MCM 41s. So, here we have to maintain some temperature, pressures and pH. So, self assembly micelle, a spherical micelle formation should be there, and with metals means silica, this type of structure formation is there, and after that if we means heat up to remove that surfactants, this type of MCM 41s support materials or materials we can synthesize, mesoporous materials. So, here you can see this is the same thing. So, here's a different way, means we have shown here. So, step by step. So, this is you can say MCM 41. So, that formations. So, how means assembly is there, condensation and then surfactant removals, this way you can prepare MCM 41s. Okay. So, here also same thing, see here iron oxide doped MCM 41 was synthesized using the same way. So, first CTAPs was used, then in waters, then micelle formations is there, and then TEOS was added for hydrolysis and condensations using ammonium hydroxide was also used, and then this type of frame or structure formation is there, and then it is calcined template removal is there. So, then this is MCM 41 formations is there by these steps. After that iron precursors was used in these materials, and then iron doped MCM formations was there, and it is calcined to make iron doped MCM 41s. This way we can synthesize metal doped MCM 41s also. Okay. So, thank you. So, we have synthesized or we have studied, so how different type of microporous, mesoporous materials we can synthesize, that is the we can use for a particular application, means catalyst synthesis that materials. So, next day we will discuss about how using these materials we can prepare our catalyst. Thank you.